Welcome! In this problem walkthrough, we're tackling a fascinating challenge, problem number 1432, titled Max Difference You Can Get from Changing an Integer. We'll explore the task of modifying digits in an integer to maximize the difference between two numbers. Let's dive in and break it down step by step. In this problem, we are given an integer called number, and we need to perform a specific operation exactly 2 times. The operation allows us to pick any digit from the integer and replace all of its occurrences with another digit. This replacement digit can be any number from 0 to 9, but there's an important restriction: the resulting number cannot have leading zeros unless the entire number is 0. Using these two operations, our goal is to calculate the maximum difference possible between the two resulting integers. The input to this problem is a single integer number, which lies between 1 and 10 to the power of 8. The output will be an integer representing the largest possible difference between the two numbers created after performing the operations. Let's explore some examples to better understand the problem. In the first example, the input is number equals 555. To get the maximum number, we can replace all occurrences of the digit 5 with 8, giving us 888. For the minimum number, we replace all occurrences of 5 with 1, resulting in 111. The difference between these two numbers is 888, 111, which equals 777. This demonstrates how replacing all instances of a single digit can yield the numbers needed to calculate our maximum difference. Now, let's move on to another example. Here, the input is number equals 9. To calculate the maximum possible difference, we can replace the digit 9 with 8, yielding the number 8. For the minimum number, we replace the 9 with 1, resulting in 1. The difference between these two numbers is 8, 1, which equals 7. This example highlights how the problem works even for single-digit numbers, where the entire number is modified in each operation. Let's look at a more complex example next. In this example, the input is number equals 1, 2, 3, 4, 5, 6. To maximize the number, we can replace the digit 1 with 8, creating 8, 2, 3, 4, 5, 6. To minimize the number, we replace the digit 2 with 0, resulting in 1, 0, 3, 4, 5, 6. The difference between these two numbers is 8, 2, 3, 4, 5, 6, 1, 0, 3, 4, 5, 6, which equals 8, 2, 0, 0, 0, 0. This case illustrates how different digits can be targeted in the two operations, allowing us to explore the full range between the maximum and minimum possible values. When solving this problem, it's important to consider several edge cases. For single-digit numbers like 1 or 9, the replacements are straightforward, as the same digit is used to calculate both the maximum and minimum. For numbers with repeating digits, such as 1111 or 555, all occurrences of the digit must be replaced simultaneously, which directly impacts the result. Additionally, for numbers like 9000, care must be taken to ensure that no leading zeros are introduced during the replacement. Lastly, for large numbers near the upper constraint, like 100000000, it's crucial to keep performance in mind while crafting an efficient solution. These considerations will help ensure your approach is robust and handles all possible inputs effectively. To solve this problem, one approach we could consider is a brute force method that systematically tries all possible replacements for the digits in the number. The intuition here is straightforward: since the problem allows us to replace any digit exactly twice, we can first replace one digit with every possible alternative from 0 to 9. For each resulting number, we then perform a second transformation by replacing another digit, which could be the same digit as before or a different one, again with all possible alternatives. After generating all these transformations, we calculate the maximum difference between the largest and smallest numbers obtained. While this approach is comprehensive, it involves a lot of computation. Specifically, the time complexity grows quadratically with the number of digits in the number, and for each digit, we explore 10 possible replacements twice. This results in a computational cost of n squared asterisk 10 squared, making it impractical for large inputs. Additionally, the space complexity remains low since the computation can be done in place, but the sheer number of iterations makes this method inefficient overall. However, this brute force strategy is not optimal. The large number of combinations it generates, coupled with the redundant calculations, makes it computationally expensive and infeasible for larger inputs. Instead, we can turn to an optimized approach that leverages key observations about the problem. The goal is to maximize the difference between two numbers, one as large as possible, and the other as small as possible. For the largest number, we replace the first non-9 digit with 9, ensuring the number becomes as large as it can be. For the smallest number, we replace the first digit with 1, provided it's not already 1, or the smallest non-zero digit with 0 to minimize its value. These replacements are applied globally, meaning all occurrences of the chosen digit are replaced, which makes the transformations consistent. This targeted strategy allows us to achieve the desired result without exploring unnecessary combinations. This optimized approach is not only simpler but also significantly more efficient. The time complexity is linear, O(n), since we only traverse the digits of the number once for each transformation. The space complexity is O(n) as well, to account for storing the string representation of the number during manipulation. These efficiencies make it a clear choice for solving the problem. By focusing on direct transformations based on specific observations, we avoid redundant computations and minimize the overhead of traversing the digits. Comparing this to the brute force method, the optimized approach is far more scalable and practical for large inputs. Other potential heuristics, such as replacing the largest digit with 0 to minimize the number, could be explored, but they lack the intuitive guarantee of achieving the maximum possible difference. This makes the chosen approach both efficient and reliable. In conclusion, the optimized approach stands out for its balance of efficiency, simplicity, and correctness. By using the replace first heuristic, we achieve the maximum and minimum transformations with minimal effort. This method ensures the solution is not only fast but also easy to implement, aligning well with the constraints of the problem. The strategy effectively avoids unnecessary computations while guaranteeing the correct result, making it the ideal choice for this problem. In this problem, we are tasked with finding the maximum integer that can be obtained by replacing exactly two digits in a given number. The replacements can be made with any digits from 0 to 9. To solve this, the first step is to parse the input integer into a string format. This allows us to easily access and modify individual digits. For instance, if the input is 1234, we convert it to the string 1234. The next step involves identifying all possible ways to replace two digits. To do this, we iterate over all pairs of digit indices, ensuring that the two indices are distinct. For each pair of indices, we explore all combinations of replacements by substituting the digits at those positions with every possible value from 0 to 9. This means for each pair, there are 100 potential combinations to consider, as each digit has 10 replacement options. By doing this systematically, we ensure that every possible way of modifying two digits is taken into account. Once we have identified a pair of indices and selected replacement values, the next step is to generate the new integer. We start by making a copy of the original string representation of the number. Then, we replace the digits at the chosen indices with the selected values. After modifying the string, we convert it back into an integer to evaluate its value. To keep track of the highest number we encounter, we maintain a variable called max_value, which is initially set to the value of the original integer. Each time a new number is generated, we compare it with the current max_value. If the new number is larger, we update max_value. Additionally, we must handle cases where a replacement might introduce a leading zero. For example, if the first digit is replaced with 0, the resulting number would be invalid. Such numbers are discarded to ensure that our result remains a valid integer. After exploring all possible replacements, the final step is to return the value of max_value, which will represent the largest number achievable through exactly two replacements. Several key insights make this approach both effective and manageable. First, a brute force method works well in this case because the number of digits in the input is usually small, less than 10 in most practical scenarios. This ensures that iterating through all pairs of indices and all replacement combinations remains computationally feasible. By systematically generating every possible combination of two-digit replacements, we ensure that no potential maximum is missed. There are important edge cases to consider, such as numbers with repeated digits, like 1111, or very small numbers with fewer than 3 digits. Another critical edge case is avoiding invalid results caused by leading zeros, which would make the number invalid as an integer. To implement this efficiently, we use a string representation for easy manipulation of digits, temporary variables to store intermediate numbers, and a single variable to track the maximum value throughout the iterations. These choices help keep the algorithm both simple and efficient. The time complexity of this algorithm is primarily determined by the number of digits in the input integer, denoted as n. To explore all possible replacements, we iterate over all pairs of digit indices, which takes n squared time. For each pair of indices, we try 100 combinations of replacements since each digit has 10 options. This part runs in constant time, 1. Combining these, the overall time complexity is n squared. On the other hand, the space complexity is minimal because we only store the string representation of the number, a few temporary variables for replacements, and the variable max_value to track the largest number. As a result, the space complexity is n, where n is the length of the string representation of the number. This balance of time and space efficiency makes the algorithm practical for solving this problem. Let's go through an example to see how the algorithm works in practice. Suppose the input is 1234. First, we convert the number into the string 1234. Next, we begin exploring pairs of indices to replace. Starting with the pair of positions 0, 1, we replace the digits at these positions with values from 0 to 9. For instance, replacing the 1 at index 0 and the 2 at index 1 with 9 and 9 results in the new number 9934. We compare this with the current maximum value, which initially is 1234, and update the maximum to 9934 since it's larger. This process continues for all other pairs of indices, systematically exploring every possible combination of two-digit replacements. After completing all iterations, the algorithm identifies the maximum value, which in this case is 9934. This number is returned as the final result, demonstrating how the algorithm efficiently determines the optimal solution. This solution computes the maximum difference obtainable by replacing digits in a given integer. The core idea is to replace digits strategically to maximize or minimize the resulting number. The function begins by converting the integer to a string for easier manipulation. To calculate the maximum possible value, the function iterates through the digits of the string and replaces the first non-9 digit with 9, ensuring the resulting number is as large as possible. This works because 9 is the highest single-digit number, and replacing earlier digits has a greater impact. For the minimum possible value, the function handles the first digit separately. If the first digit isn't 1, it is replaced with 1, as 1 is the smallest non-zero digit that avoids leading zeros. For subsequent digits, the function avoids creating leading zeros and replaces the first eligible digit with 0. Finally, the function converts the modified strings back to integers and calculates the difference between the maximum and minimum values. This approach ensures that the solution is efficient and handles edge cases, such as numbers with repeated digits or leading zeros, correctly. Here, we start by defining the maxdiff method, which takes an integer number as input. To simplify manipulation, we first convert the number into a string using integer.toString number. This allows us to work with individual digits more easily. Next, we focus on finding the maximum possible value. The approach is to replace the first digit in the number that isn't already a 9 with 9. This ensures we maximize the value of the number. We iterate through each character in the string representation of the number using a for loop. As soon as we find a digit that's not 9, we replace all occurrences of that digit with 9 using the replace method. Once this replacement is done, we exit the loop since we only need to perform this operation once to achieve the maximum possible number. The resulting value is stored in the max number variable. After that, we turn our attention to finding the minimum possible value. Here, we start by checking if the first digit of the number is not 1. If it isn't, we replace all occurrences of the first digit with 1. This replacement ensures that the number starts with the smallest valid digit, maximizing the reduction. However, if the first digit is already 1, we take a different approach, which is explained next. In cases where the first digit is 1, we need to carefully modify the other digits to achieve the minimum value. Starting from the second digit, we iterate through the string representation of the number. For each digit, we check if it is neither 0 nor 1. If such a digit is found, we replace all occurrences of it with 0. This ensures that we don't create a leading 0 or unnecessarily modify valid digits like 0 or 1. Once the replacement is performed, we break out of the loop, as further replacements are unnecessary. Finally, we calculate the maximum difference by converting the modified string's max number and min number back into integers using integer.parseInt. The difference between these two values is then returned as the result of the method. This step concludes the implementation, and the function now computes the maximum possible difference between two numbers derived from the input integer by following the described rules. We start with the input number 555. The first step is to convert the number into a string format, which gives us 555. Then, to find the maximum possible value, we iterate through each digit. The first digit encountered that is not 9 will be replaced with 9. Here, the first digit is 5, which is not 9, so we replace all occurrences of 5 with 9, resulting in 999. Next, we calculate the minimum possible value. Looking at the first digit, which is 5, we replace all instances of 5 with 1, giving us 111. Finally, we calculate the difference by converting both maximum and minimum values back to integers and subtracting. The result is 999 minus 111, which equals 888. So, the maximum difference is 888. Now, for the input number 9288, we again start by converting the number into a string, resulting in 9288. To find the maximum possible value, we iterate through the digits. The first digit is 9, which is already 9, so we skip it. The second digit is 2, which is not 9, so we replace all occurrences of 2 with 9. This gives us 9988 as the maximum value. For the minimum possible value, we check the first digit, which is 9. Since replacing 9 with a smaller digit would make the number invalid, we move to the next digit. The second digit is 2, which is not 0 or 1, so we replace all occurrences of 2 with 0. This results in 9088 as the minimum value. To calculate the difference for the input 9288, we convert the maximum value 9988 and the minimum value 9088 back to integers. Subtracting these gives 9988 minus 9088, which equals 900. Now, consider the input number 110105. First, we convert it into a string, resulting in 110,105. To find the maximum possible value, we iterate through the digits. The first digit is 1, which is not 9, so we replace all occurrences of 1 with 9. This gives us 990,905 as the maximum possible value. For the minimum possible value with the input 110105, we start by examining the first digit, which is 1. Since it's already 1, we skip it and move to the second digit, which is also 1. Skipping further, the third digit is 0, which remains unchanged. Finally, we reach the fifth digit, which is 5. Since 5 is not 0 or 1, we replace all occurrences of 5 with 0, resulting in 110,100 as the minimum value. To calculate the difference, we convert 990,905 and 110,100 back to integers and subtract. This gives 990905 minus 110,100, which equals 880805. Thus, the maximum difference in this case is 880,805. To analyze the time complexity of the solution, let's start with the basic operations. First, the integer number is converted into a string using str number. Since an integer with n digits requires processing each digit during the conversion, this step takes n time. Next, we calculate max_number. This involves iterating through each digit in the string representation of number, which takes n in the worst case. Additionally, the CRReplace method is used to replace every occurrence of the first non-9 digit with 9. This operation scans the entire string to make the replacements, which also takes n time. Combining these steps, the process of finding max_number has a time complexity of n plus n, which simplifies to n. Now, for the calculation of min_number, if the first digit isn't 1, we directly replace the first digit with 1 using strReplace. This operation scans the entire string, resulting in O(n) time. If the first digit is already 1, we instead loop through the remaining digits to find the first non-0 and non-1 digit. In the worst-case scenario, all n1 digits are checked, which takes O(n) time. Once the replacement digit is identified, we again use strReplace, which takes another O(n). Therefore, the process of determining min_number also has a total time complexity of O(n) plus O(n), which simplifies to O(n). Finally, both max_number and min_number are converted back to integers, an operation that processes each digit and takes O(n) time. Subtraction between these integers is a constant time operation, O(1). Adding up all the steps, the total time complexity of the solution becomes O(n) plus O(n) plus O(n) plus O(n), which simplifies to O(n). Let's now evaluate the space complexity. The input number is stored as an integer, which requires O(1) space. When the integer is converted into a string number_str, it requires O(n) space, where n is the number of digits in number. Two additional strings, max_number and min_number, are generated to store the modified versions of number_str. Each of these also requires O(n) space. During the conversion of max_number and min_number back to integers, temporary storage proportional to the length of the strings, O(n), may be used internally. However, this does not affect the overall asymptotic complexity. The total space complexity, therefore, is dominated by the storage of the three strings, number_str, max_number, and min_number, resulting in an overall space complexity of O(n). To better understand the efficiency of the provided solution, let's compare it with a brute force approach. A naive method would involve generating all possible numbers by replacing each digit in the input with every digit from 0 to 9. For an input with n digits, this would result in O(10 to the power of n) numbers. Each number would then need to be converted back to an integer and compared, resulting in an overall time complexity of O(n*10 to the power of n). On the other hand, the given solution avoids this inefficiency by making targeted replacements based on the problem's requirements. For best-case scenarios, such as when no replacements are needed, e.g., the input is already maximized or minimized, like 999 or 100, the loops for max_number and min_number terminate early, achieving O(n) time complexity. In the worst case, replacements are needed for both max_number and min_number, requiring full iterations and replacements. Even then, the time complexity remains O(n). Finally, let's solidify our understanding with a mathematical proof of the big O analysis. Each operation in the solution, such as string conversion, looping through the digits, and performing replacements, is independently O(n). Since these operations are executed sequentially rather than nested, their complexities add up instead of multiplying. As a result, the overall time complexity remains O(n), making the algorithm linear in relation to the number of digits in the input number. Similarly, space complexity is determined by the storage requirements for the string representation of the number and the modified strings, which are proportional to the number of digits, leading to a space complexity of O(n). This linear relationship in both time and space makes the solution both efficient and scalable. When tackling this problem, there are a few common pitfalls to be aware of. A frequent mistake is misunderstanding the problem statement itself. For example, some assume that you can replace digits more than twice or that the resulting numbers must always be unique. This can lead to unnecessary complexity, so it's crucial to carefully read the constraints and fully understand what's required. Another issue is not properly handling leading zeros. If your replacements result in numbers with leading zeros, such as turning 1000 into 0100, it might cause problems, especially when parsing integers. Double-check your logic to ensure edge cases like these are handled. Additionally, inefficient enumeration can be a significant challenge. Generating all possible replacements without eliminating duplicates or invalid states can lead to exponential growth in the solution space. Using techniques like memoization or breaking early when unnecessary calculations are identified can save a lot of time. Finally, don't overlook edge cases. Test scenarios like single-digit inputs, numbers with repeated digits, or cases where replacements don't improve the result. These edge cases can easily trip up an otherwise working solution if not explicitly considered. Now, let's talk about ignoring constraints on input size. For large numbers, relying on brute force approaches without optimizing replacements can cause timeouts during execution. It's vital to analyze the problem's constraints and ensure your solution operates efficiently within those limits. From an interview perspective, it's a good idea to start by breaking down the problem. Discussing a brute force solution initially demonstrates your understanding, and then you can refine it into a more optimized approach. Interviewers are often more interested in your thought process than just the final solution. Also, think about common patterns in the problem. For instance, when maximizing a number, replacing smaller digits with 9 is usually a good strategy. For minimizing, you might consider replacing larger digits with 0 or 1. If you're making a specific optimization, such as limiting replacements to significant digits, be sure to explain why that choice is efficient. Lastly, always walk through an example to show how your algorithm works step by step. This demonstrates clarity in your approach and builds confidence in your solution. This problem is part of a family of related challenges, and recognizing these connections can help deepen your understanding. For instance, LeetCode 670, maximum swap, is closely related. In that problem, you're allowed to replace 2 digits to achieve the maximum number, but only one replacement is permitted. Another related problem is LeetCode 1347, minimum number of steps to make 2 strings anagram. While it focuses on strings rather than digits, the emphasis on transformations and optimization skills is similar. LeetCode 31, next permutation, is another interesting example, where you manipulate digits to find the next largest permutation. Finally, LeetCode 966, vowel spellchecker, provides a broader application of replacement logic, this time applied to strings instead of numbers. Exploring these related problems can help you recognize patterns and strategies that are widely applicable, giving you a stronger foundation for tackling similar challenges. When considering alternative approaches, it's important to weigh their trade-offs. The brute force approach is straightforward to implement, as it simply explores every possible replacement. However, this method becomes computationally expensive for large inputs, with complexity potentially growing exponentially based on the number of digits. A greedy approach, on the other hand, is more efficient, often focusing on replacing the smallest or largest digits first to quickly improve the result. While faster, this method may not work well for cases where the optimal solution requires a more global strategy instead of localized decisions. Dynamic programming is another option. It tracks state changes for each digit, making it a powerful tool for problems with strict constraints or dependencies. However, dynamic programming often comes with significant memory overhead, which can be a limitation in certain scenarios. Understanding these trade-offs allows you to choose the approach that best balances efficiency and complexity for the specific constraints of the problem you're solving. Great work! In this session, we tackled problem number 1432 and explored strategies for maximizing the difference by modifying digits. Remember, algorithmic efficiency and clear thinking are key. Thanks for joining us. See you next time for more problem-solving adventures. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!